In the last lecture, we saw what is meant by a vector space. Let us recall that a vector space has 4 ingredients. 1, an arbitrary non-empty set, then a field F, and the addition or a rule of combining 2 elements in V, and what is known as scalar multiplication, a rule of combining an F element with a V element, and then we had the rules for plus and dot. Together with this we get a vector space. We shall now look at some examples of vector spaces. The first simple example is the following. Since all our motivation for the definition of a vector space stems from our experience with R k, clearly R k is itself a vector space. So, R k, which is the set of all, we want to call it column matrices such that x j belong to R, and then we have this usual laws of addition etc. So, R k is a vector space and the field is R over R. The scalars we consider are R with the laws of plus and scalar multiplication as defined earlier. How did we define this scalar multiplications? We just, when we say add, we said simply add the corresponding entries. When we said multiply by a scalar, we meant multiply every entry by the scalar. Now, what was the 0 element of this vector space? For the 0 element, the 0 vector or the 0 matrix, and for x, x1, x2, xk minus x is the negative is just minus x1 minus x2 etc. This we have seen already. These were the properties of R k which motivated us to give the abstract definition of R k. So, this is the first fundamental definition example of a vector space. The second example is we replace the real numbers by the complex numbers. So, the real field is replaced by the complex field. So, we take V to be C k, which is the set of all the vectors or all the column matrices x 1, x 2, x k, where x j are complex numbers. Again addition is entry wise, scalar multiplication is entry wise. We will call this entry wise addition and entry wise scalar multiplication as usual addition and scalar multiplication. Then we take F to be C, then V is a vector space over F, that is C k is a vector space over C with the usual laws of addition and scalar multiplication. Again I repeat, when we say usual law, it means entry wise addition and entry wise scalar multiplication. In this vector space, the 0 vector is the theta k again, which is 0 0 0, and for x, x1, x2, xk, the negative vector is minus x1, minus x2, minus x2. Since x1, x2, xk are complex numbers, minus x1, minus x2, minus xk is also a complex number, and therefore, this vector we have defined minus x also belongs to Ck. In general, we can start with any field f and look at f k. So, f is any field and look at f k, which is the set of all x equal to x 1, x 2, x k, where now x j's are from f. So, instead of f, when we put f equal to r, we are looking at r k. When we put f equal to c, we are looking at a c k. In general, we can take any field f and look at f k. Then again usual laws of addition. What does that mean? We add two elements in f k by adding the corresponding entries. Usual law of scalar multiplication, that means we multiply alpha and x by multiplying every entry of x by alpha. Then f k is a vector space over f with the usual laws of addition and scalar multiplication. And again, what is the v in this case is f k. So, what is the theta v? It is again theta k in this case 0 0 0, where now the 0 refers to the 0 element of the field f, and for x in v minus x, the negative is again minus x 1 minus x 2 minus x k. Again, since x 1, x 2, x k are in the field f, in the field every element has its negative, and therefore, minus x 1 minus x 2 minus k belong to f. When we take f equal to r, so in this example, if we take f equal to r, we get r k, the vector space r k. When we get f equal to c, when we take f equal to c, we get the vector space c k. Let us look at another typical example, which is a field which is different from all this. Let us take for example, f to be the binary field Z 2. What is this binary field Z 2? It consists of two elements 0 1, where the addition is defined by the following table: 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0, and multiplication in this field is defined as 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 1, 1 into 1 is 1. This is the simplest multiplication table that one can remember. Now, with these operations of plus and into, Z 2 is a field. So, we are looking at the field Z 2 plus and into. Now, in this field, for example, what is minus 0? Minus 0 is 0 itself, and minus 1 is 1 itself, because 1 plus 1 is 0, and therefore, 1 acts as the negative of 1 plus 1 is 0. Here is 1, when I add it with 1, I get 0. So, 1 acts as the negative of 1. So, in this field, every element is its own inverse. So, in Z 2 plus into, every element is its own negative. Now, let us look at V to be this field 3, take k equal to 3. So, f k is now 3. What is this? This is the collection of all x 1, x 2, x 3, 3 by 1 matrices, where x 1, x 2, x 3 are from the field is Z 2. That means, x 1, x 2, x 3 can be either 0 or 1. So, there are two choices for x 1, namely 0 and 1, and for every choice of x 1 there are two choices for x 2, namely 0 and 1, and for every choice of x 1 and x 2 there are two choices of x 3, namely 0 and 1. So, there are totally 2 into 2 into 2 8 possibilities. So, there are only 8 elements or 8 vectors in this collection V. What are these 8 vectors? So, actually Z 2 3 consists of these following vectors 0 0 0, 1 0 0, 0 1 0, 0 0 1. Now, this is all zeros. These three are only one and remaining two zeros. The one can be in the first place or in the second place or in the third place. Similarly, we can have two ones and 1 0, and finally, we can have all ones. So, we have 1, 2, 3, 4, 5, 6, 7, 8 elements in this field in this Z 2 3. Now, on this Z 2 3, just like the addition in R induced an addition in R k, the addition in Z 2 induces an addition in Z 2 3. So, V equal to Z 2 3 is a vector space over Z 2, the field is Z 2 with usual laws of addition and scalar multiplication. Now, what do we mean by usual laws? We have to add entry wise. When we add entry wise, each entry is a field an element in the field Z 2. So, it has to be added according to the Z 2 addition laws. For example, if we add 1 0 1 and 0 1 1, according to this usual laws, it should be 1 plus 0, 0 plus 1, 1 plus 1. Now, these pluses here refer to the plus in Z 2, but in Z 2 1 plus 0 is 1, 0 plus 1 is 1, but 1 plus 1 is 0. So, this is what we meant by usual laws. You have to add entry wise, but the entry additions are done according to the field laws. Similarly, there are only two scalar multiplications possible, either multiplication by 0 or multiplication by 1, because the field has only two elements. When we multiply by 0, all the entries become 0. When we multiply by 1, all the entries remain the same. This is what is meant by saying that we are looking at usual laws of addition and scalar multiplication. So, in this field, so in this vector space Z 2 3 over Z 2, this is a vector space, this is our V, this is the field A, and the laws of addition and multiplication, scalar multiplication are there. So, this is the vector space. What is the 0 element of this vector space? It is obviously 0 0 0. Now, something tricky happens here. If you take any x in Z 2 3, its corresponding negative vector must be, I must take minus x 1. We have seen that in the field Z 2, every element is its own negative. So, minus x 1 will be x 1 only, minus x 2 will be x 2 only, minus x 3 will be x 3 only. So, this is in this particular vector space, every vector is its own negative. For example, 1 0 1 plus itself. Since this should act as its negative, we must get 0, but what is it? 1 plus 1, 0 plus 0, 1 plus 1, but in this field 1 plus 1 is 0, 0 plus 1 is 0, 1 plus 1 is 0, and this is what theta v is. So, thus this is a vector space which has only a finite number of vectors in it, 8 vectors, and in this vector space every vector is its own negative. When we deal with vector spaces over finite fields, we get such very peculiar things which we are not familiar with when we are talking about our usual notions of vectors. Let us look at now some more examples. So, in general we have seen that f k is a vector space over f. Now, this takes care of the basic extension of the idea of R k. From R k we got the general notion of a vector space, from R k we went to C k, from C k we went to F k, and these were the examples of the various F k's. Now, we will go to the notion of matrices. The next example we will look at is, let us start with R and look at all m by n matrices whose entries are real numbers. So, these are all the matrix spaces, they are all matrices A I j where there are m rows and n columns, and all the entries are real numbers. So, let us consider all the matrices, real matrices with m rows and n columns, and let us take F to be R. Now, we know how to add matrices, again entry wise addition. We know how to multiply a matrix by a scalar. Every matrix is, every entry in the matrix is multiplied by the scalar. We will call this the usual laws of addition and scalar multiplication. V is a vector space. What is V? R m cross n is a vector space over F. What is F? R with usual laws of addition and scalar multiplication of matrices. So, we have the vector space of real matrices. What is the 0 element of this vector space? It is the 0 matrix with m rows and n columns. We will use this. So, in this vector space the 0 element is the 0 matrix, and if A is a matrix in this vector space, then what is minus A? Minus A is a matrix obtained from A by taking the negative of each element. So, it is minus A I j 1 less than equal to I less than equal to m, 1 less than equal to j less than equal to m. So, we have the vector space of all m by n real matrices. In particular, if we take m equal to n, we get the vector space of all square matrices. So, R n squared is the vector space of all n by n real matrices over the field R. Analogously, just like we took R here, we can take complex numbers. So, we have C m cross n, the set of all complex m by n matrices is a vector space over the field where field is complex numbers. Again, what is the 0 element of this vector space? It is the 0 m by n matrix, and the negative of a matrix is just minus A I j as before. In general, we can take any f and look at all m by n matrices whose entries are from the field f. So, take a field f like we could have taken Z2. So, we will be talking about binary matrices, matrices with whose entries are only in 0 and 1. So, we take any field f, consider all m by n matrices over f, and then this is a vector space over f. Again, when we say with usual laws, that means we must add the matrices by adding corresponding entries. When we add corresponding entries, that must be according to the rule of addition in the field f. So, it is usual laws of addition and scalar multiplication. Once again, in this vector space, the 0 vector is the 0 m by n matrix, and minus A is minus A I j, where the minus A I j has to be taken as per the negative rule in the field f, and in general we can have the rectangular from the rectangular to the square matrices is the vector space of all n by n matrices over the field f. So, first we had the vector space of k by 1 all the entries from a field f, then we had the vector space of all matrices m by n where the entries are from a field. The field can be R, the set of real numbers, the field can be C, the field of complex numbers, or the field f can be any general field. So, now we look at another set of examples, useful examples. Let us now consider any set S. So, S is an arbitrary set S, and let us consider the set of real numbers. So, we have an arbitrary non-empty set S, and we have the set of real numbers. What is meant by a function from S to R? By a function f from S to R, we mean a rule which associates with every number S an element which is a real number f s. So, with each element S in S, a real number f s is associated. Such a rule of association is called a function from S to R. So, let us take a function from S to R, and suppose I have another function which associates G S. So, in other words, we have a function f which associates the value f of s with an element s, and G is another function which associates the value G of s with s. Now, f s is in R. Note that the value of the function is in R, the value of the function G is in R. Therefore, f s is a real number, G s is a real number. So, we can add f s and G s. So, we will get, when we add f s and G s, we will get f s plus G s, and that is also a real number. So, we have added the real number f s and a real number G s. Now, we can think of a new function which associates with s the value f s plus G s. We call that as the function f plus g. So, we have two functions from S and R, we have this sum function, and since we are adding the value at each point to get the new function, we call this addition of functions as pointwise addition. This is what is meant by pointwise addition of functions. That is, at each point the value of the functions are added. So, we now know how to add two functions from S to R. Similarly, let us take S and let us take R, the real numbers. Again, suppose I have a function f which with each S associates the value f of s. Now, f of s is a real number, and suppose I choose any real number alpha, I can multiply f of s and alpha, because alpha is a real number and f of s is a real number, and the result of the product is again a real number, because the product of two real numbers is real number. Now, we can think of a new function which associates with each s the value alpha times f s. We call it the function alpha f. This gives us the scalar multiplication of functions. This is again pointwise multiplication. So, addition of functions is defined as pointwise addition, and we have pointwise scalar multiplication. At each point the value is multiplied by the scalar. So, now we know how to add functions and scalar multiplication. So, now we consider, let S be any set, any non-empty set, let us denote, and so that is our V. Let us take f, the field, to start with the real numbers, and let us take the V to be the set of all functions which map S to R. We will actually denote this by f s R. So, this f says collection of all functions, what is the domain S, and where do they end up with, what is the value taken, it is a real number. So, it is the collection of all functions from S to R. So, we have now the set V, we have the field, do we have the plus? Well, if you take two functions, we have seen what is meant by addition, pointwise addition. So, the pointwise addition. So, what is the definition? F belongs, G belongs to FSR, F plus G by definition is a function, its value at any point is defined to be value of f at s plus value of g at s. So, we have the addition operation and we have the scalar multiplication pointwise, pointwise scalar multiplication. What does that mean? We have alpha in R, f in G, f in FSR, then alpha f is the function, by definition its value at any point s is alpha times f of s. So, we have the set V, now we have the set V, the field f, the set V is the collection of all functions from S to R, real valued functions on the set S, and the field is the field of real numbers. Addition of functions is pointwise addition, scalar multiplication is pointwise scalar multiplication. Now, with these laws of addition and scalar multiplication, FSR is a vector space over R. What is the 0 element of this vector space? It must be an element of V, therefore, it must be a function from S to R, which function theta is that function from S to R defined as at each point S it takes the value 0. That is the 0 element of this vector space or the 0 vector of this vector space. Now, if F belongs to FSR, what is minus F? Now, since F belongs to FSR, we want minus F also to belong to FSR, because the negative of anything in V in a vector space must be back in the vector space. So, minus F must be a function. So, minus F is that function which is defined as minus F at any point S, its value is take F's value and take the negative of that. The value of F is given because F is in given, we are trying to find the negative of F. The moment you know F, at any point evaluates its value, that is a real number, take the negative of that real number and therefore, you get another real number. So, that real number is called the minus F of S, it is called the value of the function minus F at the point S. So, we have the collection, the vector space of all functions from S to R. Let us look at some very specific examples in this. Suppose I take S to be a finite set S1, S2, say Sk. Suppose I take F to be a S to be a finite set and I look at FSR. Now, what do we mean by a F in FSR? So, if I have a function F which is in SR, that means F is a function from S to R. If F is a function from S to R, F will assign a real number to each element in S. Therefore, F will assign a real number to S1, F will assign a real number to S2 and F will assign a real number to Sk. So, we will have Fs1, Fs2 etc. Fsk will all be real numbers and therefore, they are k real numbers. So, we can form the usual k row matrix 1 column Fsk. So, essentially we see that these are such a function can be identified with an element in Rk. So, basically therefore, when you have S in as a finite set S1, S2, Sk, the FSR, the collection of all functions from S to R is essentially the collection Rk. We will see more in detail about this, such sort of identifications at a later time, but basically therefore, FSR in this case can be identified. We will talk about this identification in more detail later with Rk. At least we see it is such a function is only an element of Rk in disguise. Next, let us look at another simple version. Instead of the finite set, let us look at a discrete sequence S1, S2, S3 etc. So, we have now an infinite sequence S1, S2, S3. Now, look at the set of all functions from S to R. What does this mean? This means if f belongs to FSR, this means that f assigns f is a function of mapping S to R, which means f assigns a real number with S1, again f assigns a real number with S2, a real number with S3 and so on, and therefore, we get Fs1, Fs2 etc. real numbers. Thus, we get a sequence of real numbers. Therefore, we get a sequence, infinite sequence of real numbers. And therefore, in this case when S is equal to S1, S2 etc. an infinite sequence, the FSR is basically identified with sequences of real numbers. So, thus when we are talking about RK, thus when we are talking about RK, we are really talking about, in other words, functions from a finite set S1, S2, Sk to real numbers, and similarly when we are talking about infinite sequences of real numbers, we are in other words talking about functions from an infinite set, infinite sequence S1, S2, S3 to the real numbers. So, these functions and these vectors, column vectors can be identified with each other. Now, let us take S to be an interval on the real line. This interval can be a finite interval or the full real line, semi infinite, closed, open, whatever type. So, let I be some interval on the real line, and let us take the collection of all functions from I to R. So, this is the collection of all functions which with each point in the interval I associate a real number. Thus, we have the collection of real valued functions in R. Now, for example, we may take I to be the interval, for example, 0 to pi or I to be 0 t. Now, these are the types of functions we will be looking at when we talk about periodic functions and Fourier series. We may think of I as minus infinity to infinity, the whole real line. These are the type of functions which we will be talking about when we talk about Fourier transforms, and so different types of intervals will produce different types of situations which will be useful to us in our applications. Now, among these functions which are mapping I to R, there are some of very particular interest. In all the above examples, we can replace R by S. So, we can write similarly, let S be any set, any non-empty set. Then look at FSC, the collection of all functions which map from S to C, the collection of all functions from S to C, then if the laws of addition and scalar multiplication are usual, again point wise, the values are added point wise. The collection of all these functions is a vector space over C with the usual laws of addition and scalar multiplication. So, we have the collection of all real valued functions, we have the collection of all continuous complex valued functions. The domain S can be a finite set or an infinite sequence or a continuum like an interval on the real line. Now, among these class of functions there are some special ones which are very useful. Now, let us look at the situation where we have S to be an infinite sequence S1, S2, S3, and then let us look at FSR. FSR is the set of all functions from S to R or C. So, in order to keep both options available for us, let us now write F, where F is equal to R or F is equal to C. So, either we consider real valued functions on S or complex valued functions on S, where S is an infinite sequence of points S1, S2, S3, an infinite set, but it is a sequence. The elements can be arranged in the form of a sequence. For example, you can think of S as the set 1, 2, 3, 4, 5, the set of all positive integers. Now, consider the set S and the set of all real valued or complex valued functions in this. Now, if you take any function f in S, any function in FSR, so we have f mapping S to f. So, either a real valued function or a complex valued function. Take any such function, corresponding to this we get the values Fs1, Fs2, etc., which is a sequence of real or complex numbers depending on whether we take f is equal to r or f is equal to c. Now, what we do is we look at the absolute values of this. Now, if f is a real valued function, Fs1, Fs2, Fs3 are real numbers, but they can be positive or negative real numbers, but once we take modulus we get only non-negative real numbers. If f is a complex valued function, Fs1, Fs2, Fs3 will be complex numbers, but when we take the modulus again we get to complex valued non-negative real numbers. Now, let us add all this. We get summation say j equal to 1 to infinity mod fj Sj. Now, this sum may be finite or infinite, because we have now a infinite series of non-negative terms. The infinite series may or may not converge, it may diverge to plus infinity. So, we would like to look at functions where this sum is under control. So, we are going to look at all those functions. So, this may be less than infinity or it may be equal to plus infinity. So, we are going to look at all those functions which are under control, that it is less than infinity. So, we are going to look at all those functions from S to F, where again I remind that F can be R or C, such that summation j equal to 1 to infinity mod f s j is less than infinity. The sum is the sum of the absolute values is under control, okay. It is under it is finite. So, consider the set of all functions. This is called L 1, we will use the little L 1. Let me write this carefully. This is now denoted by L 1 S to R, L 1 S to R. So, this is the space L 1 S to R. So, it is not all functions from S to R. Among the functions from S to R, we only choose those functions for which this sum is finite. For example, if we take f mapping S to R or F to F defined as f s j is equal to 1 by j square. The value taken at the point S j is the square of the index j, reciprocal of that. So, now what is mod f j? Then this implies mod f j is just 1 by mod j squared, j may be, j is real. So, it is just 1 by j squared. So, what is mod f s j all added up? It is this series, and we know that this series converges, and therefore, it is less than infinity, and therefore, this function belongs to L 1 S R. On the other hand, if we take f mapping S to R as f of S j is 1 by j, then mod f s j is again 1 by j, j is an integer, and therefore, summation mod f s j, j equal to 1 to infinity is summation j equal to 1 to infinity 1 by j, which diverges to plus infinity, and therefore, this f is not. Or f, let us take a general f, f can be real or complex. So, therefore, we have some f's in mapping from S to R are in this L 1, some f's which are not mapping from S to R not in this L 1. This L 1 consists of all those functions which are from S to R, for which this total sum in absolute value is in control, it is finite. With this notation, then L 1 S f we can verify is a vector space over F. So, the set of all real valued functions on S for which the sum is finite is a vector space over R. The set of all complex valued functions for which this sum is finite is a vector space over the field of complex numbers. Analogously, instead of asking summation mod f s j, j equal to 1 to infinity to be finite, we can look at f for which summation j equal to 1 to infinity mod f s j squared is finite. So, we denote this by L2 SR. Remember, S is our discrete infinite set S1, S2, S3 etc. to be all those functions mapping from S to R for which the sum mod f s j squared is finite. For example, we had if f mapping S to R is such that f s j equal to 1 by j, then f was not in L1 SR. But now this function is such that summation mod f s j squared j equal to 1 to infinity is summation j equal to 1 to infinity 1 by j squared, because f s j is 1 by s j, and this we know is a convergent series. Therefore, this f belongs to L2 SR, whereas and f does not belong to L1 SR. So, these are two different objects, L1 SR and L2 SR are two different objects. Similarly, you can replace R by C, we get the complex functions. So, therefore, L2 S F, where F is R or C, is a vector space over L2 is a vector space over F with the usual laws of addition, because we know how to add functions, we know how to multiply a function by a scalar, these are all pointwise, and with that these. So, these are functions from S to F which have special properties. First we considered all functions from S to F, that was a vector space over F. Then we considered all functions over S from S to F for which the summation mod f s j is finite, and we got L1 SF. Then we considered all functions from S to F for which summation mod f s j squared is finite, and we got the L2 SF. Similarly, let us look at L1. Similarly, first thing is look at any interval I in R, and then look at all functions from I to R, or you look at any interval in R, or look at all functions from I to C. So, either real valued functions on the interval I or the complex valued functions on the interval I. Then this is a vector space over R, this is a vector space over C. Just like we considered special functions above where the sum was finite or the sum of the squares was finite, here we can consider functions for which the integral of the absolute value of f is finite and the integral of the absolute value of f squared is finite. So, we get L1 S to R to be the set of all functions from S to R, where S is now the interval I such that integral mod of f t dt is well defined and is finite. Of course, we must make sure that the integral is finite. We will not worry about giving formal definitions of the integral at this stage. Similarly, L2 SR, when S is the interval, is the set of all f from S to R such that integral I mod f t squared dt is finite. These are some of the important vector spaces of functions. We shall see some more vector spaces of functions as examples in the next class.